Are you all there?
Yes, sir.
Yes, Avidya.
Okay. So I'm going to share a question. Okay. So you guys can just try on your own and let's discuss after some time. Is that okay?
Yes, sir.
Yeah. I hope you can see this, right?
Yes, sir.
So a process contains two kind of cascaded transfer functions. Okay. And the question is asking, of course, first part is whether will the process exhibit overshoot, and the second part is what is approximate value of y, u is transformed to y, and what is the last is what is the maximum value it can occur. Last question, of course, you may not be able to do it. Simulate and plot. So we are not talking about anything simulating at the moment, but I think you can attempt A, B, and C for maybe 10 minutes. 10:30 we can discuss. Is that fair enough?
Yes, sir.
Yeah, but my sincere request is please solve by yourself. So just hearing, of course, you could, but I think I prefer that you solve and kind of that would give more insights. So yeah, start. So we will have a discussion maybe after 6-7 minutes. Please try on your own. Okay, so anyone? I hope you could able to complete the solution. Do you need more time, or we shall discuss the solution? What is that you need? I think let's discuss the solution. Okay, can someone volunteer and explain what are the potential ways to solve this problem?
Hello.
Yeah.
Uh, Sir, I don't know the exact procedure, but what I did was I expressed the value of ys in terms of the transfer function and multiplied by us, and then I took the inverse Laplace to find the exact value of y. So, is this method
Okay.
right?
Okay, so let's keep many options in the table, no? So one is what you have done, I understand. So you calculated the y of s by u of s. Okay, then you did the partial fractions, then took the inverse, correct?
Yes, sir.
So that would give you what? Y of max. So what that might give you to calculate the maximum value of y, maybe, correct?
Yes. Yes,
So
sir.
how do you solve the question A?
Sir, I haven't gone through that part very clearly, so I simply used the brute approach to solve this.
No, no,
The
this is
B
not
part.
brute. That is whatever you have done is exact. No, this is the exact way of, like, exact in the
Yes,
sense,
sir.
what you call, there is no approximation involved, but that would, some points might be missing here. But I think whatever you have done is one way to do it. So any other kind of suggestions from anyone? One way.
Sir, estimate.
Yes, Ishika.
Yes, sir. So, sir, using the approximation, we can convert the point one tau system into a time delay.
Okay.
So it will turn out into a simple second order system where we can calculate things using the tau and damping coefficient.
Okay. So can you keep it bit more precise?
Sir, basically, what I thought was like we can actually approximate the point one s plus one thing into e to the power minus point two s. So it will convert to a time delay thing,
Perfect.
and we will get the transfer function as k2 into k1 into e to the power minus point two s upon 4s square plus 2s plus 1.
Okay, okay, cool. So can you screen share your solution and present to everyone? Have you solved it by
No,
paper?
sir, actually, I haven't solved it on paper, but I just went through the approach, like what we can do.
Okay, cool. So let me share the screen. Okay, this is what. So this is actually one what you call one nice way of solving it. Whatever she has done. Just give me a minute. Okay. So did you anyone followed what Ishika mentioned? Could anyone follow what Ishika, the method that Ishika mentioned? Okay, so I'll just give a brief what she has told. Okay, so I'm also not going to solve it in full, but I think I'll just show the steps. I think that should be good enough. I think. So give me a minute. That's my screen. Is my screen visible to all of you? Correct?
Yes, sir.
Yes, sir.
Okay. So, so let's try to write down the question. So what we have given is u1, then it is going to a g1 transfer function, then it is going to a g2 transfer function. This is, I think, problem 6 point. 2, 3. No? This may not be true in your version of the book, but whatever. And finally, you are getting y. Okay, I think what Vinayak did, both of them has merit. So what Vinayak did, if I understand, so of course, according to the product rule of transfer function, u become directly g1, g2 now, then y, correct? So which essentially means that your y by u is g1, g2. Of course, I am excluding the s, everything has s in it. And to find out the maximum value, what he did, I'll tell you. So, so it is given that u is step change. Okay, so y would be g1, g2 u. Of course, u is step change, and you know the transfer function values of. It is unit step change or what it is written? Assume that it's
Sir, is a unit.
yeah, unit step change. So y would be g1s, g2s, and 1 by s for the step change, and you can calculate y of t by taking inverse of L inverse of y of s. Any doubt on this? This is one approach to get it. And what you will get y max. But still difficult to get. You will get y of t. Then to get y max, you may have to take dy of t with and take derivative. So have you done that, Vinayak? Or you put t is equal to infinity? What did you do?
Sir, I put t equals infinity because it involved exponential function, so that makes sense.
So that is one way of. So this would give you y, of course. I'll not say y max. This is definitely not y max. What you are getting is y infinity. Y max would be different. Why I am trying to say is, let's say if you are looking at a second order transfer function, okay, and and second order underdamped transfer function. So this is the final response looks like. Any doubt on this? This is maybe y and this is time. Y by k more y whatsoever. Any doubt on this?
No, sir.
So this is y infinity. Correct? Anyone? Any doubt? But what is y max here?
Sir, at time TP. Y at time TP.
So we should be very careful in mixing up both of them. So that is one aspect. So now what Ishika mentioned. So let's look at that in a slightly more careful fashion. So give me a minute. Okay, so I think just let me know if I am making any mistakes in numerical. I am looking just from the book and writing on this. So it is k1, k2 divided by, so of course this is very clear that we want to take the product of the transfer function. This part is at least very clear because by transfer function rules, if there are two transfer functions in series, you will take the product. So k1 by k2, then 0.1s plus 1 whole square, and next one is 4s square plus 2s plus 1. Okay, so let's consider this as term 1 t1 and this consider as t2, which is the term 2. Okay, so now look at t2 first. So what is the value of tau here? Yes, go ahead.
Sir, 4.
No, tau square is 4, tau is 2.
Tau 2.
Correct, no? And what is the value of theta? 2 theta tau is I think 2. Okay. Then
Sir, 0.5.
is 1, then theta is 0.5. So now look at the term 1. The term 1 is 0.1 s plus 1 whole square. Okay, and what is the value of tau here?
Point one.
theta. So this is critically damped transfer function. You see, how do you write this? If something can be written as like this is technically a critically damped transfer function. So your zeta would be 1. Agreed or what?
Yes.
So now let's look at, so there are now competing two competing terms that kind of, forget about the k1 k2. K1 k2 I'll write as k, some constant. So there are two competing terms that kind of governs the overall dynamics. Okay, one with a lower time constant, one with a higher time constant. So generally, if you look at the approximations, what we have looked at in the complex process, what we generally do is we'll keep the terms with the higher time constant intact, okay, and the terms with the lower time constant you would approximate as time delay. This is what I think Ishika also told. So what would happen in that case? Let k we will retain. The higher time constant guy is here now, 4 square plus 2s plus 1, I think. If there is a mistake, please correct me. Okay, so now you have this guy term. So this would be now converted as a time, what we call time delay term, so that it would be overall a second order system with a time delay. And you know how to convert this 0.1, so it is 1 by tau s plus 1. So this 0.1 become e raised to minus 0.1 over here, and the second time become next e raised to minus 0.1. So overall this theta become 0.1 plus 0.1, which is 0.2. So the approximated transfer function is e raised to minus 2.2 s by 4s square plus 2 zeta 2s plus 1. Okay, so now this is your G of S. Now one thing that you should understand, okay? Let's go and see how the profile of the system looks like. So what is it? So let's say this is a second order system. Okay, this is case 1. Okay, so this is a typical second order system. How a second order system with time delay works? Let's say if you have a time delay of theta. Will it have an impact on the maximum value, peak, anything? Will it have an impact?
No, sir.
So it only thing, yes. So as you rightly pointed out, technically there won't be any effect. What would eventually happen is your time would be delayed by certain amount theta, then it would again take off and do all this business. Agreed or what? So what are we trying to say? The critical parameters like overshoot, so this is of course an overshoot, decay ratio, etc. is not affected by time delay. So now let's take our transfer function again, k into e raised to minus, I think 0.2s for s square plus, I think 2, what is that? 2 zeta tau, right? 2 zeta tau plus 1. So for all practical purpose regarding the maximum, etc., you only need to look at this term, because this would just adds in the delay. This would adds into the dynamics. Agreed or not agreed? Anyone, any doubt? Vishnuda, Vinayak, is all clear? Deepak?
Yes, sir.
Bhavya, Dinesh, Hemant?
Yes, it is clear.
Cool. So now I'll stop. So I don't go. So now you can, now what? You can of course have the expression of overshoot. Okay. Because you only need the value of zeta, right? So with the value of theta, you calculate the overshoot. And overshoot is only this much. So you will need to add the steady state value to the overshoot. Now, how do you get the steady state value? It is K times M. Correct? So why? So what are we plotting here? This is Km times Yt is what we originally plotted. If it is a normalized variable, it is Yt by Km. So you should calculate that. So and what is overshoot basically? Can you tell me what is overshoot? How do you define overshoot?
Sir, A by B.
Okay. So A by B is this much. Let's say A by B you calculate and got is this much. And what you really need is the summation of A and B, which you will be able to get it from the overshoot. You have to just solve this and get it. So that would give you the Y max value. Then what was the question? Anything left? Is this clear or what? Any question on this? Approximately when the maximum value occur? So give me a minute. So if you look at a typical second order dynamics, okay, let's say it is Y by Km, and this is T by tau. So I am referring to some figure in your textbook. You can go back and even notes you can check. Okay, it go like this, like this, and most likely, okay, this would be like 4 or approximately close to 4. Okay, and the second would be and this would be kind of settling down probably after 16th or something. So let me just show this to you. Is my screen is okay? My screen is of course is not visible. So let me just unshare this. And let me share this. You have seen this, huh? This figure, most often. Correct? Any doubt on this? So what you can say that oftentimes the responses generally become maximum between 3 to 4. Look at this, between 3 to 4. So let's say it is 3, and you really know the value of 0.5 as the time constant. It may be somewhere here. So you can approximate it, like it could be between 3 and 4. So somewhere here, this may be 3, and it will go the maximum, and you will get it. So you can easily say that your T by tau would be close to 3 times your y-axis, correct? From which you will be able to calculate back the T max. Is that okay? Is this clear or what? Anyone?
Yes, sir.
So yeah, so this, if you are see the, you have to understand the problem in the sense that if you are looking for so if you are looking for a final response t infinity, y infinity, etc., uh, then it is always good to do this inverse Laplace transform business, and it would give you an exact answer. But if you are looking for properties like overshoot or time at which the point become the what you call overshoot, then when you take the inverse Laplace, you would get little information. So it's always good for you to convert them into a standard second order form and do the analysis. That is the take home message. Is that okay?
Yes, sir.
Yes, sir. Perfect. So maybe we'll take up one more small problem, huh?
Yes, sir.
Give me a minute, huh? Okay, so can you see the new question that I have added? Again, a similar problem. Okay.
Yes, sir. It's visible.
Yeah, so you can take 3-4 minutes and like at 10:55 or so. So please solve it. This is just for your solution thing only. So please solve it, and someone of you can explain how you have done it to the whole batch. Okay, can someone tell me how do you deal this problem? Anyone? Hello, am I audible?
Yes, sir, you're audible.
Yes, someone, Hemant, Vinayak, Ishika, Ashutosh, Nikita, Robin, Deepak, Sudeep, Dinesh, and Vishruta. I think all of you are here. So can someone tell me how do you solve this problem? Any leads, please?
Sir, leaving the highest time constant, we can approximate other into time delays, and the
Absolutely,
second largest can be divided into half.
that's absolutely fine. So let me just, so I'm just unsharing and probably let's share my whiteboard. So there are two aspects to this question. One is direct, one is very direct, which you have learned, you know how to do it. And second part is not really direct. So, okay, the first part of the question is to approximate. Correct, no? Are you able to follow?
Yes, sir.
Approximate, so you are given with a very complex G of S. It contains, let's say, K by, I think, tau 1 to tau 4, I guess, right? There are 4 time constants. And the first part of the question is approximated as first order plus time delay. So which we will use Kojestad's method. Hello?
Yes, sir.
So that's not quite straightforward. So I think you know that algorithm. You have to take this what we call the second largest time constant and approximate. And I'm not going to do that. So I think this is pretty straightforward. So then what you will get is you will get a G approx S, right? Which would be first order plus maybe tau approx. It's not tau approx, in fact it is tau only, but let me just write it that it's a new term. So I'll just say tau s plus e raised to minus theta s. Any doubt on this on how to do? This is very clear. Your notes would give you answer for this. So what about the question? Of course, question B is impossible for you to do, that requires a graph. But how do you solve question C? Can someone give a lead? Of course, it's slightly long.
So could you please show the question again?
Pardon?
Could you please show the question again?
Yes, I'll do that. Let me share. Visible?
Yep.
Huh? Visible or what?
Yes, sir, it's visible.
So B part is of course a simulation problem which you might not do, but how do you solve the C part?
Sir, I think after we've approximated the model in A part, then we can calculate what's the actual model that we will get the function for y, and basically minimizing y actual, maximizing the value of y maximum, y actual minus y approximated.
Absolutely. So have you understood the question? It is asking when is the maximum error of two response. So
Yes, sir.
yeah. So I think Vinayak told a method. So let me just share my whiteboard again. Slightly involved though, but I think so. Is my screen is visible? Not yet. I think.
Not now.
Give me a minute. It should be. Yes, na?
Yep.
So we have now two g of s. One is true g of s, and other one is what you call g approximate s of y. So now what you are asking is what would be the maximum error? How do you get the maximum error? It's not very easy to get from any of this. First of all, it is fourth order, one is first order plus time delay. So you have to do this, do an inverse Laplace, and you'll get g of t. So g of s would give you g of t, correct? And approximate g of s would give you approximate g of t. Agreed or what? So this is the error. And to how to you wanted to maximize this error. So what would you do? You take the dE by take the derivative approximately equal to 0, and at the point where it is maxima, you figured out that. Is that okay? Is this clear or what?
Sir, I think there might be some problem in this approach.
Okay. So
Because
what is
let's say the value of maximum value of this particular function is 0 and the minimum is -3, then our answer should be minus the mod of -3, which is 3. But if we calculate the maxima, I think we'll get 0 or something like that. So shouldn't we like square it and then
it's
derivative,
done?
then take
I
the
just
derivative?
Yes, I already put it now. I forgot to put a square. You have to put a square or put an absolute.
Yep.
But the problem is if you put absolute, you will have difficulty in taking derivatives. So square is much more easier. Okay. Okay, guys. Any questions? So if not, I think let's close the class. And Ashutosh, do we need to meet in the afternoon?
Sir,
Are
I
you
don't
there?
think so. Anyone will come. If someone had to come, then they must have been in this class.
Okay, cool. So I think that should be fine then. All the best. Do well in your exam. And if you have any doubt in the meanwhile, please write to me or write to the TAs. We shall be able to help you. Okay, guys. Bye-bye. So I am leaving from the meeting and closing the closing the session. Bye-bye for you. Bye.